of example on large scale, small scale hydrogen production, and then show you where we are at the moment. So as for the introduction, I'm working in Eindhoven. It's in the south of the Netherlands. Netherlands is very small. Anyway, every time we present, I present our lab. I say our labs because in the last 10, 12 years, I'm working quite close to Tecnalia in Spain, in the north of Spain, San Sebastian. And actually what we do is a very strong exchange of material, people, labs, and so on. So what I show today is something that we developed together with Tecnalia in the last 10 years. And I believe that in April or May, you got also a presentation from Alfredo Pacheco, who is the researcher in Tecnalia. I collaborate on membranes. Now, what we do in our group, as I told you, the group is called Inorganic Membranes and Membrane Reactors. So membranes is quite a big team. But we work in general on integration of reaction and other functions. So membrane reactors are integration of reaction and separation. What we do also is chemical looping, like here in this scheme, is a combination of reaction and separation, where the separation is done by a solid. In what is called chemical looping, the solid is a metal, which is oxidized, so it's taking the oxygen from the air, and then is releasing the oxygen in another reactor. You can also think about a solid that instead of taking oxygen takes CO2, so you have absorption, a separation via absorption, and then you release the CO2 in another reactor. And another theme we are following is the integration of reaction and energy management, and this is a picture of a plasma reactor where basically we supply the energy to a reaction in a form of a plasma. In this way, you can carry out the reaction that normally occurs at very high temperature, also at room temperature. So what we do normally is a combination of proof of concept and modeling in our group. Now, if we look at the presentation of today, I will give you examples of these two and not on the plasma. And if you look at the membranes, we start from a very small scale, also designing new kind of membranes. Then we do a little bit of scale up, and then mostly in Tecnalia we do the larger scale up. So what you see here is a bundle of 125 membranes for hydrogen production. Now, as I told you, we collaborate a lot with Tecnalia. So if you want to do a separation in Eindhoven, we do a little bit of material and more on the reactor. In Tecnalia is the other way around, more on the material and a little bit on the reactor. And together we cover quite a lot of application. CO2 capture and hydrogen purification or hydrogen production is quite a big theme. And what you see here, we start again, as I said, in very small scale up to large scale production. Now, coming back to the hydrogen, what is our driver to do this research on integrated reactor? I believe that you know this kind of graph, which is reporting the CO2 concentration in the atmosphere. And I'm quite sure that I don't need to convince you that this concentration is also responsible for climate change, the climate change that we see. So this picture is also a very famous one. Of course, we have to care about environment and we have to care about animals, but we are also very pragmatic because all the water is going somewhere. And if you recall the picture that I showed you before, and you look at the models for calculating where the water is going, here is the Netherlands, and you see that most of the Netherlands will be underwater if we don't do anything. Now, what is the solution to this problem? There are several solutions, and I want to list three of them. One is reduction of the number of people. So we have to consider that most of the problem we have is that because of too many people living in a way that is not sustainable. Now, of course, this is not a solution we can work on. What we can work on is the reduction of the use of fossil energy, or perhaps using renewable and improving the efficiency of also fossil fuel. And another solution is capturing the CO2. And this, of course, you can do a capture in the point where you produce the CO2. In the long run, I think we have to do also capturing of the CO2 from the atmosphere. Now, solution 2 and solution 3 is where we can do something. If we don't do anything here, obviously the F will do something on solution 1. So the long-term solution will be taken automatically if we don't do anything. Now, who is the responsible for all the pollution and the emission of the CO2? There are different reports. I take the reports of IPCC. You can find several reports. It's not important the number. What is important is the division of the contribution. So roughly you have 1/4, which is related to agriculture. So to make the agriculture automatic, but also the fertilizer production. One part is the transportation and building, one part is industry, and one part is electricity production. And if you zoom in the electricity production, of course, you do electricity production because of people living in the buildings, for industry, for agriculture again, and for energy in general. So basically, these are the responsible. Actually, it's very strange to say that industry is responsible. So a few years ago, when I was producing some slides for a presentation, I used to go into this nice website. There are a lot of questions here. If you answer this question is about your standard of living, then the calculator will tell you how much you are contributing to the emission of the CO2. And when I did this presentation, was a couple of years ago, this was my result. So the calculator told me that I would finish my energy, my share of energy, the 21st of February. And if all the people would live like me, basically we would need 7.1 Earth. So the resources of 7.1 Earth. Now, this is was funny because my presentation was the 22nd of February. So I finished the energy the day before. In any case, if you go and look into these numbers, again, you see that the share is more or less similar to what I showed you before. For me, it was a lot of mobility because of a lot of meetings and a lot of travels. And the rest was, again, agriculture of food and the use of goods and services. So more or less as in the report of IPCC. So when we say that industry or transportation is responsible, we have to take care that we are the responsible because we are using transportation and we are using the goods produced by industry. So we have to do something. And if you look here, if I could work on sustainable fuels, for example, this would decrease, or a better way to produce fertilizers. And in production of fertilizers, hydrogen is also part of it. So if you can improve the efficiency there, the amount of CO2 and the amount of impact would decrease as well. Now, a few years ago, there was a nice paper in Nature. The paper is called the 7 separation that will save the world. Now, again, don't look at the numbers, also because this number was corrected in a follow-up paper. What is important is that also in US, this was for US, the share of energy is more or less the same as I showed you before. So industrial is the biggest part, then you have transportation, commercial, and residential. This paper took the industrial one and showed that up to 55% is due to separation. And of this separation in industry, up to 50% is given by thermal separation, so distillation, drying, evaporation. And the author calculated that if you could make a transition from this thermal separation to another type of separation, in particular to membrane separation, they did in this paper, you would save up to 90% of the energy. And as I told you, saving energy means also decreasing the emission of CO2. And what is a membrane? Today I will show you quite a lot of membranes. A membrane is a separation layer that separates two phases and allows only a few components to pass through the membrane. So the membrane should be selective. Now, if you take a membrane, you can have different use of these membranes. One is separation, what I just told you. Another use can be contacting. You can use a membrane, for example, to make a contact between a liquid and a gas. Think about absorption. Normally, the absorption is done in packed column or tray columns. Why we use membranes? Simply because the area, the contact area, when you use membrane contactor, can be 1,000 times or 10,000 times bigger than when you have a very simple vessel. And of course, the contact area is one of the components for the transfer of material between the two phases. That's why you can use a membrane contactor. And then if you play with the material of the membrane and the pressure of the two phases, you can make sure that the contact occurs only on the membrane. Then you can use immobilization, where you use the membrane to put a catalyst on it. Generally, the immobilization is more for when the catalyst is an enzyme. And you can select a membrane such that the enzyme stays there, but stays also active. And another possibility is to have a controlled release of a component. Think about a pill where the external of the pill is a membrane, and the membrane releases the drug in a controlled way. Think about a reactor where you can control the release of one of the reactant, for example. Now, if you take any of this function and you put a reaction close to it, then you have a membrane reactor. So you can combine reaction and separation. For example, this mixture could be a mixture that is reacting, and you can separate one of the component from the reaction zone. So a membrane reactor or an integrated reactor would be, in this case, a vessel where you have a catalyst where the reaction takes place and membranes where the separation takes place. And this separation can be a separation of the product or can be a separation of a reactant that enters the reactor. In this particular case, is biogas to produce hydrogen. What we work on is a separation that allows hydrogen to be separated from the reaction mixture. Now, does a membrane reactor or an integrated reactor work? There are several studies showing that this works. A typical one is this of my colleagues in Italy. They show that for a particular reaction, which is water gas shift, which is quite interesting for us because it's for hydrogen production. If you take a conventional system, let's say as a reference 100%, then if you take a membrane reactor, you can decrease the volume and the amount of catalyst up to 30–20%, depending on pressure, depending on the temperature that you use in the membrane reactor. So it looks that it's working. Now, you have to consider that when you integrate two functions in a single reactor, like in a membrane reactor, in an absorption-enhanced reactor, what you are getting is that you integrate function in a single system, so the single system is smaller than two systems separated. On the other end, when you have the two systems separated, you can optimize, let's say, the reactor and the separation. So both can be optimal. If you combine, they have to work at the same condition, which means that either the membrane or the catalyst is working in suboptimal condition. So to use an integrated reactor and to be more effective, you should have a reaction that has some problem. If you don't have any problem in the reaction, any challenge in the reaction system, it doesn't make sense to integrate. And when you have some challenge in a reaction system, basically when you have equilibrium reactions, you know that you can optimize the catalyst as much you want, but the maximum you can reach is the conversion at equilibrium. And if you separate, in this case, a product, let's say hydrogen, in the hydrogen production, then you can, at the same condition, get higher conversion. So you can enhance the conversion by separating one of the components. The same is here. If you have one component that can react and be separated and react, then you can increase the conversion. Another way to use a membrane reactor or an integrated reactor anyway is when you have a problem of selectivity. Imagine, for example, if you have a series of reaction and your component of interest is an intermediate. For example, if you have oxidation reaction, you want to do a partial oxidation and you want to achieve high conversion of the component A, you have an high possibility that your partial oxidized A, so C, is still reacting with oxygen to produce CO2. So if you can remove this product, then you have an enhancement of selectivity. So takeaway message, if you don't have any challenge in your reaction system, it's better not to integrate function in a single reactor. On the other hand, if you have a challenge, it's better to integrate. In any case, you have to calculate if your new reactor and new system has a production cost that is lower than the previous production cost. Now, since we are discussing hydrogen production, we are in this particular case because all the hydrogen production reactions, at least the thermal reactions, are equilibrium limited. So in this case, if you can separate something, and in particular hydrogen, then you can get an increase of conversion. Now, I want to give you two examples related to these two pictures. And if we want to put these pictures in words, this is the first sentence I like a lot, which says that hydrogen and stupidity are the two most abundant material in the universe. The only problem we have is that hydrogen is not concentrated on Earth. So we have to produce hydrogen. And the other one is coming from the book of Jules Verne, which describes hydrogen as a source of heat and light. What is written here, I would say electricity and heat. And I will show you something related to this. So everything is about hydrogen production. Now, if you take the standard way to produce hydrogen, this goes through a system of different reactors. Most of the hydrogen is produced by natural gas. So normally, natural gas is mostly methane. Normally, what we have is a very high temperature reactor where the methane reacts with steam and produces hydrogen and CO. Then we have to convert the CO to additional hydrogen. So we go to lower temperature and we go to the water gas shift. That's why I show you the previous study on water gas shift. Once you have to convert, you converted the CO, then you have to separate the hydrogen. And of course, the most pure hydrogen you want, the more off gas you have from your PSA. And then the off gas you use together with additional methane to drive the first reactor. So you burn in a burner, and then you produce quite a lot of CO2. So normally, when you start from natural gas, you get from one side pure hydrogen, from the other side you get a lot of CO2 in the atmosphere. And of course, this system is quite efficient, simply because, first of all, people don't care about CO2, and then also they integrate the complete system with the steam production, and steam is or electricity is also a co-product of this big hydrogen production system. Now, if we take this as a reference, what we want to do is to produce same amount of hydrogen, or at least in the same condition, and get rid of the CO2 emission. In that case, you can have hydrogen production without influencing the climate change. Now, if we take the methane reforming, just for simplicity, let's take a single reaction. Later, I will show you the system of reaction. What you see immediately is that you have methane, you have water, and this is an equilibrium reaction. It's quite endothermic, that's why you have to go to high temperature. Now, if it's an equilibrium reaction, what you can do is to integrate reaction and separation to improve the conversion and perhaps improve the conversion at lower temperature. That would be very good. Now you have two possibilities here. One is to separate the CO2. And what you do to separate the CO2, normally in real life for this kind of temperature, the only thing you can do is separating the CO2 with a sorbent. So you have sorption-enhanced reactors. The other way is to separate the hydrogen. And the hydrogen you can do in different ways. You can do also with sorption, but what we work on is separation of hydrogen with membranes. So we have membrane reactors. Now, if you separate the CO2 or you separate the hydrogen, you have the same effect. So you are removing a product, so you are shifting the equilibrium. The difference between the two is that if you separate the CO2, then the CO2 is more pure, the hydrogen is less pure, you have to purify. On the other end, the hydrogen remains at high pressure, so you have driver to purify the hydrogen. If you separate the hydrogen, then you have the hydrogen that is more pure, so you don't need other separation for the hydrogen, but the CO2 is not 100% pure. So if you need the pure CO2, you have to additionally separate the CO2. And the CO2 remains normally at high pressure and the hydrogen remains at low pressure. Now, let's start with the first one, which is the sorption-enhanced reforming. And let's look in more detail the reaction that occur for hydrogen production, which are the steam reforming and water shift. What I said before, this is high temperature and this is low temperature. Both are equilibrium. So if you are able to remove the hydrogen, you can improve the equilibrium. If you are able to remove the CO2, you improve this equilibrium and automatically improve also this because you remove CO. So you shift also this equilibrium. Then these are equilibrium, as I said, highly endothermic because the summation is 165 kilojoule per mole. To force the equilibrium towards hydrogen production, you can remove by hydrogen, but what we discuss now is remove the CO2 and how you remove the CO2 with a solid, and the typical solid is calcium oxide. So if you have calcium oxide and CO2 in some concentration, then you produce calcium carbonate. So you take calcium oxide, reacts with CO2 to produce calcium carbonate. This is highly exothermic reaction. So it's also helping you because the heat that is produced by this is driving the steam reforming. So in total, you have an energy neutral reaction, and this is the total reaction. Of course, seems too nice to be true because you remove the CO2 and you get also the energy required for the steam reforming. And indeed, every time is something looks very good, there is a catch. In this particular case, you can see immediately, if this is the reaction, calcium oxide is a solid. So you have a number of moles of calcium oxide in your reactor. Sooner or later, this calcium oxide will be transformed to calcium carbonate. So what you have to do, you have to regenerate the calcium carbonate to release the CO2 and get back the calcium oxide. Now, if this reaction is very exothermic, this is very endothermic with the same amount of energy. So you have to add the energy to get the calcium carbonate releasing the CO2. In this particular project, what we do is we use a chemical looping system with copper to supply the energy for this calcination reaction. So how the loop is working, you have the calcium, the calcium that is taking the CO2, the copper that is supplying the energy. So we have to find out how much copper and how much calcium we can put in the reactor to get hydrogen production and to have the regeneration of the calcium. Now, the copper is used because by reaction with hydrogen and CO is exothermic, so it's supplying the energy to the calcium oxide. To the calcium carbonate to become calcium oxide. And of course, again, once the copper is reduced, you have to regenerate the copper, and you can use with air, because this is the reaction that occurs. Copper plus oxygen, you have again copper oxide that you can use in this reaction here. Now, if you take all this reaction and you want to put in a reactor system, what you have is 3 steps, at least 3 steps. And what you have is that in the first step, the fuel is reacting with in gas phase, and the calcium oxide is taking the CO2. So basically you have hydrogen without CO2. Then you have to oxidize the copper. And then after you oxidize the copper, you reduce the copper. The copper oxide is releasing the energy and is calcining the calcium carbonate and is producing the calcium oxide. Now, this is a nice process that was developed by our colleagues in Spain, Abanades in particular, and we worked together in a project to demonstrate this concept. Of course, you have sorbent, you have copper. In the project, we worked on sorbent development, copper development, and also on the integration of the two. And in particular, in our group, we worked on the reactors and the demonstrator. So we did the system of steps such that the complete system would capture the CO2, produce the hydrogen, and then regenerate the solids. And I told you before that you need at least 3 steps, but in reality, you need 5 steps. And now for simplicity, believe me that you need these steps. And then in particular, if you have any question, I will show you how these steps would work. So you have a system of reactors. One reactor is working for hydrogen production. One reactor is working for copper oxidation. One reactor is working for calcination of the copper oxide, of the calcium carbonate to calcium oxide, and then you switch the gases between the different reactors. Now, what is important is that the calcium oxide has to be able to capture the CO2, and of course, this is an equilibrium reaction. So it depends on the temperature and the concentration of CO2. So if the concentration of CO2 is higher than the equilibrium concentration, then you have capture. If it's lower, then you have release of the CO2. And this is the equilibrium conversion, the equilibrium concentration. And you see that this equilibrium concentration depends only on the total pressure and the temperature. So if you take this function here, you can see that, for example, at 1 bar, if you are below 900 degrees, you need a partial pressure of CO2 more than 0.01 to get the capture of the CO2. If you have a lower pressure, then you have a release of CO2. So you see that going from here to here, you go from calcium carbonate to calcium oxide. And of course, it depends on the pressure. So you can also play with the pressure such that you have more or less calcium carbonate or calcium oxide. So using this and using a model of the different reactor, you can calculate which pressure, which temperature, and which amount of calcium oxide you need in the reactor. And this is what we did. The calcium oxide that we need in the reactor depends, of course, on the temperature, depends on the pressure. And the best we found is using at 0.2, so 20% of calcium oxide in the system. So if we have 20% of calcium oxide in the system, the amount of hydrogen, the total amount of hydrogen that we produce is a little bit lower than in other cases, but it's more pure. You see that the purity of the hydrogen, 95%, is the most of the hydrogen that we produce. If we put more calcium oxide, then again, we decrease the hydrogen production, and we decrease also the purity. So this is the amount of calcium oxide that we need. And then we need a similar amount of copper to regenerate the calcium oxide. Then based on this calculation, we did also a demonstration. This is a reactor that we have in our lab. It's a quite big reactor. We can put up to 7 kilos of material. And we did the demonstration. And you see here what we produce is when we start, we have pure, more or less pure hydrogen, 95%, which is the maximum we can reach with this concept. And then when all the calcium oxide is getting calcium carbonate, then the purity decreases. And at the end, when all the calcium oxide is calcium carbonate, the maximum we can have is the equilibrium concentration of CO2, of hydrogen. And the same here, at the beginning, 0 CO2, then slowly increases because the calcium oxide is decreasing. And then at the certain point, the CO2 is constant because all the calcium oxide is calcium carbonate, so you have only steam reforming. What you see here is that the same trend you have after 285 cycles. Of course, the cycle is this plus the regeneration plus the regeneration of the copper, and then start again. This is the number of cycles. So we did up to 300 cycles, and then we use the data, these are experimental data, to validate the model. And finally, as I told you before, every time you have a nice reactor, please do also the techno-economic analysis, because the system seems to work. You have to make sure that the system is cheaper, or the production that you do is cheaper than the standard production. In this particular case, we did a techno-economic analysis for using this system as power production. So we produce hydrogen, and then we use hydrogen for power production. And of course, you have to take care of all the components in the system. And at the end of the day, what you have to do is to compare with the benchmark. So if you take a benchmark, which is using natural gas to produce power, you see that the efficiency is this. If you capture the CO2, then the efficiency decreases. And with the new system, the efficiency is this one. So the efficiency is not extremely better than the standard benchmark with CO2 capture. I show on purpose this because, as I told you, not every reactor that looks better than the standard is at the end of the day better. And in this particular case, for power production in this condition, our new reactor looks nicer, but is not nice in terms of efficiency, and is not nice in terms of cost. So in this particular case, you would never invest in this particular reactor to produce electricity. Of course, we have also cases in which the new reactor is better than the standard one, and in particular when you produce hydrogen for other application is better, but not for electricity. Now, let me give you, we saw the sorption enhanced reactor. Let me give you some example of membrane reactor. And I still use the chemical looping, which is the link between the two parts of my talk. And the chemical looping, just to remind you, is using a metal, which reacting with air is producing a metal oxide. And then this metal oxide is releasing the oxygen and is reacting with the fuel. What is very nice is that the reaction between the metal and the air is always exothermic. So when you do this reaction, you have nitrogen from one side and this very hot metal oxide. And this very hot metal oxide, then you can use to drive, for example, a steam reforming. So if your fuel is methane and water, you have the so-called chemical looping reforming, and you produce CO and hydrogen. So what I did a few years ago is to use this system together with membranes, and I developed this reactor system in which we use the metal to get metal oxide, so to get very hot material and to supply the energy to the steam reforming. And we use the membrane to produce hydrogen, and to make sure that this reactor works at lower pressure. So if you, at lower temperature. So if you take a black box around the system, you feed air, you feed methane, you feed water, you get hydrogen, CO2, and you get nitrogen. The only difference is that if you zoom in, then you have hydrogen pure from one side, nitrogen pure from another side, and CO2 pure from another side. So you have hydrogen production pure with CO2 capture in a single system. And just to give you an idea, we started this product in 2012, and we took 5 years to reach a TRL 4 to 5, which means testing this reactor with cycles in lab scale. So we had to do this reactor system, and here you see a few pictures of the two reactors. They are connected because the solid has to circulate, and then there is a big tube here going up, 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 up. Then there is the cyclone to separate the gas and the solid. The solid goes down, down, enters the second reactor. Here we have the membranes where we separate the hydrogen. So the solid is circulating, and from one side we have hydrogen, from the top here we have the nitrogen. Now, does this work? Of course, we have to test with membranes, and the membranes that we use in this particular case is based on palladium silver. I saw a few people connected that are very good in producing membranes, and this particular membrane was around 5 micron thick. These are the picture of the membrane. And if you look at the experiments, what you see is that steam reforming is occurring here. Here is without membrane, I mean with the membrane closed, so I'm not extracting the hydrogen. What is nice with steam reforming is a very fast reaction. So you reach the equilibrium very fast, it's relatively stable. Then when you open the membrane, the hydrogen decreases because I'm extracting the hydrogen. The methane is also decreasing because I can convert at the same temperature much more methane. And the CO2 is increasing because, of course, I remove hydrogen and I produce CO2. Then you see also quite a lot of fluctuation in temperature, which is very good for us, because in this particular point of the reactor is where the solid are moving. So when you see fluctuation, it means that the solid are moving inside the reactor. When this particular temperature is stable, then the solids are not moving, so you don't get this very nice results. Then we did a lot of experiments. We took the data to validate the model. And at the end of the day, of course, again, you have to do a techno-economic analysis to make sure that the new reactor looks nice, but the proof is that the reactor is good, is that the hydrogen cost is lower than a conventional reactor. These are fluidized beds. So to do this particular analysis, we had to develop also models in Aspen to do fluidized bed membrane reactors here. So if you open our Aspen, you have also models for membrane reactors. And then we did the techno-economic analysis, and that we want to show you again the conventional hydrogen production. Very high efficiency. The cost is this €1 per cubic meter. Of course, this cost depends on the cost that we put for electricity and for methane. If you choose a different cost for methane, of course, this can go also to 0.15. So what is important is not this number, is the comparison. So if you take a conventional, this is the cost. If you want to capture the CO2, at least you have to capture 75%. In this particular case, we capture 74%. And the cost, you see that is increasing. With the new reactor, the efficiency is still the same, and the cost is very similar. But you capture 91% of CO2. So in principle, today you could produce hydrogen with CO2 capture at the same cost of the hydrogen without CO2 capture. So looks very good. But of course, this is based on results at TRL 5. And what we found out is that, of course, there are always some problems, or some challenges, I would say, and in particular with the membranes in this case. What you see here is a test of membranes for almost 1,000 hours. What we found out is that for many hours, the membranes are very stable, but at a certain point, and especially at high temperature, what's happening is that after 800 hours, this membrane, the selectivity drop from 200,000 to around 2,000. For this particular case, we need a selectivity of 12,000, which means that the membranes were not good enough after 1,000 hours. And of course, if you have a plant, you don't want to stop the plant every 1,000 hours. Take-home message is that you have to test the membranes, or you have to test the system for a long time to make sure that the system works. And in this particular case, these membranes that we used didn't work. What's happened is that this is the surface of the membrane. You see something happening on the surface, such that the selectivity is lower. And this can be because of the temperature or because of the catalyst that is moving inside the reactor. So based on these results, we develop a new membrane. So the challenges become new research question. We go back to the lab and we develop this that we call double skin membrane, where we have the support, we have the selective layer. So up to now is a standard membrane. We put the protective layer on top of it such that the particle cannot touch directly the selective layer. And what we found out is that if we take a membrane without selective layer, look at the selectivity, you start from 10,000 and go after 1,000 hours goes to 1,000. And if you start with the selective layer, first of all, the similar membrane, the selectivity is much higher and is much more stable. And here we increase temperature, decrease temperature, stop fluidization. This is always in fluidization. So as I said, challenges will give you opportunities for new research, but also very important when you work with membranes, make sure that you test the membranes for a long, long time. If we stop at 100 hours, all the membranes will work. And perhaps our colleagues can also confirm this. You start to see membrane failure when you work for a few hundred hours in the lab. And now, just to finish, I told you that I want to show you also small scale, and in particular, connected to what Jules Verne was saying, combining electricity, power, and heat. So what we have here at the moment, at least in Europe, but also in US, we have in our house, we have a boiler to produce heat, and we take the electricity from the cables that arrive at our home. Of course, this electricity is produced somewhere in a power station, and then during the transportation, you get a lot of losses. So if this is the amount of energy that you use, and in the standard way with transportation of electricity, this is the energy that you have to put in the system, simply because you have a lot of losses. So what about using a system that can produce electricity directly in your house? Then you see that you have not much losses, and generally when you produce electricity, you produce also heat, so you can use the heat directly in the house. And you see that for the same amount of energy that you want to produce, then you have much less fuel. So higher efficiency, less fuel, less CO2. And this is coming from US, this picture. So in the past, we did a few projects to demonstrate this system. Here are the projects that just if you want to find out what we did. But the trick was always the same. So if you want to do a cogeneration of heat and power, there are different systems on the market. And all the systems start from natural gas and use a PEM fuel cell. At least the system that we investigated use a PEM fuel cell to produce the electricity. Now, if you start from natural gas and you want to use a PEM fuel cell, you have to produce the hydrogen. So you know already from what I told you before that you have a lot of steps up to hydrogen purification, and then you can feed your PEM fuel cell. Of course, if you use a membrane reactor, you can take all these steps in one. In a membrane reactor, you can produce hydrogen and go to the fuel cell. So in the different project, what we did in Refor cell, we just tested that this is possible. In ferret, we took different natural gas compositions to see if the membrane reactor would resist a different concentration. And then in fluid cell, we took out the natural gas and we start with ethanol. Now, let's go to the proof. And the proof is when you have a conventional system and you have a new system, of course, the new system looks better because you have a single reactor. All the rest from the fuel cell looks the same, but you have a single reactor. So it looks much better already. But what you have to do is to calculate if the efficiency is better. And of course, also the cost. So what we did is calculating the efficiency of the conventional system. We divided in 4 parts just for visual reference, just to show that if you take the new system, which is this, and you divide it in the same 4 parts, the PEM fuel cell, the heat recovery seems the same, a lot of differences in the fuel processor, a little bit of difference in the steamer. And if you do the calculation, what you find out is that the conventional system with a lot of reactors has an efficiency of 34% calculated, which is quite in line with what you find in the brochure of the vendors, because the brochure of the vendors have an efficiency ranging between 32 and 35%. So this calculation shows that the model works quite well. And if you take the new system with the membrane reactor, the efficiency, which has only a single step, the efficiency goes to 43%. What is important here is to say that it's not the number of steps that is increasing the efficiency, but the decrease of temperature between the conventional system and the membrane reactor system. Why I can decrease the temperature? Because recall that in the conventional system, you have an endothermic reaction, which is equilibrium, so you have to go to very high temperatures to get the conversion. In a membrane reactor, you can stay at 600, 550 degrees and still have all the conversion that you need. And this jump of 200 degrees gives you a jump of almost 10% in the efficiency, which is quite a lot when you speak about electrical efficiency, by the way. And now, also in view of time, the steps that we took, I told you that we worked together with Tecnalia since 2010. We started with very small membranes. In the years, we increased the length of the membrane. We did the first fluidized bed with hydrogen production with less than 10 ppm of CO, which means that the hydrogen can go directly to fuel cell. We did a membrane reactor with ethanol. Then we reached the first big membrane reactor with the target of the reactor, of the market. And we designed the 2 cubic meter prototype, and then we went to 20 cubic meter prototype. And after that, we spin off the production of the membrane to a company. And in between, we had several European projects. And if you want, allow me, these are a few pictures. You see that we start from a very small membrane. We increase the length of the membrane, small reactors, then put more membranes in the reactor. Then we did the first milestone, 1,000 hours again of pure hydrogen production. Then I would say poor people scale up. We took small membranes and put together to get longer membrane. And then we start working on, together with people working on the supports of the membrane to longer membranes. And you see that more and more longer membrane in the reactor, up to 125, and the reactor gets bigger and bigger. And when we reach here, this is the maximum we can put in our lab. So we spin off the system to a company. So there is a company now developing this. And in the meantime, we have several projects also with some of you as partner, where we do hydrogen separation with membranes, hydrogen production with membranes, also from different liquids, different gases, and we do also CO2 hydrogenation with membranes here. And of course, as I told you, we also work, I show you something on chemical looping. This project is producing Fischer-Tropsch fuels with chemical looping. At least chemical looping is one of the steps. And then a lot of projects on plasma, and combination of membranes and different reaction engineering. And with this is all I have to tell you today. Thank you very much again for the invitation. And if there is any question.
Thank you so much, Fausto, for your time and a very exciting talk. My name is Ludo Dumay from Khalifa University, and I will lead the question time. So if you have any questions, please raise your hand, or so that Fausto can see when you are ready to ask, and then we will take questions as they come. In the meantime, while maybe people gather your thoughts, because your talk was very comprehensive as well. So you mentioned the decay of the membrane performance over time, and that's clearly, like you mentioned, a major issue both in water or in gas separation per se. Have you looked maybe in details at the material stability? Because obviously you look at extreme conditions compared to water or other types of separation processes. So what do you believe right now are the major hindrance to developing materials or membranes that can last for tens of thousands or more hours per se? What are your high-level insights in this field, please?
Yeah, I think indeed we are testing the membrane in extreme conditions. One of the projects is Macbeth. We have to test the membrane reactor for 8,000 hours. Actually, we have two prototypes. Both of them should work for 8,000 hours, and 10,000 hours is the minimum. We can really go to the market. In all the techno-economic analysis that we did, we assume that we have to change the membranes every 2 years. So if the lifetime is lower, of course the cost becomes higher, and then you are out of the market. So that's a minimum that we have to reach. We know that if we are able to decrease the temperature a little bit, then the membrane stability is higher. If we are able to work below 500 degrees, then we have many thousand hours without any degradation. We believe that we solved the problem of fluidization with this protective layer. A little bit is helping also in the thermal stability, because the palladium is less mobile in that condition, but is not still good enough to reach 2 years of lifetime. So the main thing we have to do is to try to do the design of the reactor such that we are still able to work at below 500 degrees. And then we are already good enough for the market. For example, if you take the reforming or the cracking of ammonia, which we carry out at 420 degrees or even 400 degrees, then there is no problem at all. For water gas shift, there is no problem at all. Reforming of methane, yes, is a little bit problematic. Ethanol, the same, because ethanol becomes methane at high temperature, then you have the same problem of reforming of methane. So I think temperature is the main problem. Of course, we are also working on different materials, but unless you put electricity in, which is one of the research lines that we are doing, but if we do only pressure-wise, the palladium membrane is still the one that is more efficient for this separation, for the hydrogen.
So when you say electricity, you mean looking at electrocatalytic reactors in a sense?
Yes.
Yeah. Thank you. Oh, that's great. Any questions from the audience for Fausto? Maybe another one from me then. So I think you talked about the cost, obviously, of production in terms of amount produced cubic meter per dollar or potentially per kilowatt hour. And I was just wondering, are you looking at integration or coupling of some of your systems with renewable energy sources. It will not change the output of your system, I understand, but it might potentially reduce the carbon footprint of some of the some of the aspects there. So I was just wondering if that's one of the aspects that in the school or in the department you're also considering as an integral approach to the carbon capture, for instance.
Yeah. For some reactor, we are working just to connect with renewable electricity, for example. If you look at the hydrogenation of the CO2, is exactly trying to match the reactor performance with the electrolyzer performance, so to have fluctuation also taken into account. If you look at the membrane reactor for methane reforming, no, we are not considering that as connected to in an integral way, because normally what you use there is either just for hydrogen production, so extremely large scale, or, for example, the company that we created is looking for small scale hydrogen production in the order of 300 or 500 cubic meter per hour, which is a refueling station. So you have methane arriving and you produce the hydrogen for a refueling station.
Okay, thank you. That's very clear. Any question for Fausto? I have one last one, if not. It's not more like asking for a piece of advice, because clearly you have been able to develop materials, potentially with collaborators, but nevertheless get down to very high TRL levels. And do you have any advice for potentially early career researchers or postdocs who are starting their career there and who are interested to bridge that gap from fundamental or applied materials to something that can scale up? If you have any tips for them or anything you would like to advise them to do, that'd be great.
Yeah, I think especially for young researchers, they have to look at scientific excellence. The bridge to higher TRL is important because there you see if your material is working. But for a young researcher, it's better to focus on scientific excellence, especially because when you do a scale up, is too big for small scale, so for lab material, and is too small for industrial material. So every of this reactor that we do at TRL 5, 6 is so expensive, it's taking so much time, simply because the material do not exist. If you want a pump, for example, if you take a pump for your lab, it's very easy. For industry, it's very easy. But for our reactor, we spent 1 year to find a pump that could work.
Right.
So it's not extremely easy. On the other hand, look always to when you develop something, look always to the real cost of the final product that you do, because everything looks nice because it's new, but sometimes, as I show you, I show on purpose something that looks extremely exciting with a lot of material inside, and then at the end of the day, it's more costly than a standard one, so nobody will put money on it.
Yep, that's a good advice. Thank you so much. Well, if there is no other questions for Fausto today, I would like to thank you once again for taking the time in your very busy schedule to join us. And if you were able to share with us maybe your slides, I would circulate them to those who are interested and actually would like to keep a copy.
Yeah.
So thank you so much, everyone, for joining. Thank you, Fausto, for your time, and I wish you all a very nice and safe day. Thank you.
Thank you very much.